All right, good afternoon, everyone. So let's get started here. Um, so I want to make a correction on problem number 1 on the homework 11 here. So the angular velocity omega should be, let's change it to 1.5 radians per second, not the 3 originally. I posted. Okay, I already updated the file. If you have downloaded this already, you can just make a change there. If you print it out, you can cross out the 3 and then make it to 1.5. Okay, so it turns out if you use 3, the normal reaction on B is going to be negative. Okay, so which is not the case. Okay, so use 1.5 instead of 3. All right. Today we'll be looking at chapter 18 on kinetic energy, work, and principle of work and energy. Okay, so we will have 2 lectures on this chapter, so today and Friday. Okay, and then I'm not going to have a new lecture on Monday next week. Okay, so you guys can use that time to study. Okay, for the exam on the Tuesday, the final. Okay, so so let's get started here on today's lecture here. So again, we'll be starting with the reading quiz here. Okay, so go ahead and then do the reading quiz. Okay, send me your answers in the chat privately. All right. All right, so we'll take a look. The first one says the kinetic energy due to rotation of the body is defined as. Okay, so if you are looking for kinetic for rotation, then it's 1/2 moment of inertia times omega squared. Okay, so this one should be C. All right. And the second one here, when calculating work done by forces, the work of an internal force does not have to be considered because, that is because for each of internal force, there should be a counter pair, okay, of it that is in the opposite direction. So the work will cancel out by the internal forces because they come in pairs, okay? So that would be B, all right? So I think everyone got the 2 answers right. Okay, so good job on that. So let's take a look on the lecture part of the day. So I feel like this is kind of review of what we learned earlier. So on the kinetic energy. All right. So but we have both. In this case, we'll consider both rotational kinetic energy and the translational kinetic energy. Okay, which we did separately earlier. um, so and then this is the case of if we have plane motion. Okay, so in this case the kinetic energy T is equal to 1/2 mv squared. So this is due to translational of center of body, center of gravity of the body, and then plus 1/2 Ig omega square. Okay, that's the rotational kinetic energy. All right. If the object, the body is only having pure translational motion, then you only have the first term 1/2 mv square. Okay, and if it only has the rotational um, motion, okay, without having translational motion, then for example, if this body is rotating about the axis O, all right, so there's no translational motion of the body. So then if you look at the center of the gravity here, the kinetic energy is equal to 1/2 mvg square. Okay, so this is from the linear motion of the center of body. Okay, so there's a linear motion of it, and then there's this rotational motion of it. Okay, so you still add the two, and then if we are writing this kinetic energy, all right, so rewrite the first equation here. So you take the 0.5 out. MVG square will be the so okay, so VG is equal to R times omega. Okay, in this case, R is the distance from point G to O. All right, so if you do that, you will realize that this is going to be equal to 1/2. Okay, um, M times R square. Okay, which gives you the moment of inertia about 0.0. Okay, plus mr square. um, Actually, the first one in the square bracket here is comes from the ig in the second term in the first equation. Okay, so you actually take the 0.5 out and then take omega out as well. Okay, now keep in mind vg is equal to rg times omega, and then you take the square out. Okay, so the second term in the square bracket is the m rg squared, which is coming from the first term in the first equation. Okay, so in that case, ig plus mrg squared in the square bracket, according to parallel theorem, then this is the moment of inertia of the body with about the exit O going through O, point O. Okay, so then kinetic energy can be written as just purely in forms of rotational motion. Okay, so this is about the rotational axis. Okay, so T equals to purely the rotational energy. All right. um, so if the rotation is about occurs on the about an axis going through G point, okay, so in that case, then V will be becoming 0 because V is equal to R times omega. In that case, R is 0. Okay, so then you only have rotational energy about the exit going through point G. Okay, so then the first equation on this slide becoming just the second term. Okay, so the first term in the first equation here vanishes, so then T is just equal to the rotational energy. Okay, so that's when you can just consider just the pure rotational energy, kinetic energy. Okay, all right. For kinetic energy, we learned that principle of work and energy. So which says the work done should be equal to the change in the kinetic energy. Okay, so basically, for energy, it's defined as the F times dr, and then due to integration of it. Okay. So and then so we take the cosine of the angle theta, which is between the force and then dr, okay, because only in the direction of the displacement, that component of the force will do work. The component of force perpendicular to the displacement will do zero work, okay? That's where the cosine theta term is coming from. Couple special forces, the work done, a couple of special forces. One is the weight. So work done by weight is equal to minus W delta Y. Okay, so because the weight is only in the vertical direction. Okay, so then if you do F times dr, then you are going to just focus on the y component. Okay, so then delta y or delta r will be just you would just take the delta y. Okay, so and then work is always pointing downward, so you get a minus sign there, minus w. Okay, or the gravity is always pointing downward, so you get that minus w over there, indicating the direction. Work by a spring force, all right, so then it should be equal to the energy change of the spring force. Okay, so from the final position, kx final square minus ks initial square, or ks1 square minus ks1 square, okay, with a factor of 1/2 in front. Okay, so 0.5 there. All right, so this is the work done by the spring force. Sometimes so internal forces, they always do zero work because they come in pairs. Okay, so one force will do a positive work, then its counter force will do exactly the same work but minus. Okay, so internal forces, the work done by internal forces, they will always cancel out. But sometimes some external forces also do zero work. Okay, so for example, if the force is perpendicular to the displacement, then the work will be zero. Okay, so normal forces usually will do zero work because normal force is usually is perpendicular to the direction of the displacement. And now friction force, if you have static friction, then it will do zero work, because if there's static friction, there's not relative motion the contact surfaces. Okay, so then dr is zero because dv is zero, so dr is zero. Okay, in that case. All right, so then implies if you have a wheel or a disc that's rolling without slipping, then the friction force should be static friction in that scenario. So then the friction force will not do work. Okay, so for the example of if you have a car that is moving without slipping, then friction force will do no work in that case. Okay. All right. Now, work can also be done by couple moments. Okay, that means if you have force or several forces, they will have torque on the body, and then if under torque the body is rotating, okay, with some angular displacement like d theta, so the torque or couple moments times d theta, if you do integration of that, that will give you the work done by moments, okay, or torque. Um, torque, the work will be positive if moment and the change in the displaced angular displacement are in the same direction, okay. Otherwise, the work will be negative. So then putting all this together, we will have principle of working energy here. So initial kinetic energy, all right, that should include rotational energy and translational energy, kinetic energy. Okay, think about both forms. Sometimes you would have rotational kinetic energy to be zero. Sometimes you might have translational kinetic energy to be zero. So that's the initial kinetic energy plus the work done. So work done coming in different forms. You can have work done by forces. You can have work done by moment couples or torques. Okay, so be careful about to include all the work done by different forces and then torques. Okay, that should equal to the final, okay, or T2 final kinetic energy. Okay, so that's the principle of working energy here. Now keep in mind, because we are talking about energy, energy is a scalar form, it doesn't have direction. Okay, so this equation is a scalar equation, so which will make things a little bit easier. All right, so that's the main content here for the lecture. So let's take a look on the concept quiz over here. Let me create the breakout rooms for you guys to join. Okay, so 3 breakout rooms, and then randomly assign. I have the rooms open now. You guys can join the rooms and then work on the concept quizzes here. All right. So let's take a look here on the first one. I think the first one is easier. So you guys all got that one right. So the first one says if a rigid body rotates about its center of gravity, its translational kinetic energy then will be zero, right? Because it only rotates with the center of gravity. So then V in this case will be zero because R is zero. Okay, so the first one, that's zero. Okay, you got that one right. On the second one here, it says a rigid bar of mass M and length L is released from rest in the horizontal position. What's the rod's angular velocity when it has rotated through 90 degree? Okay, so in this case, the rod is original in the horizontal position over here. So and then final position will be in this vertical direction when it rotates 90 degree. Okay. So we can apply principle of work energy. So we can do um, kinetic energy initial plus the work done equals to the kinetic energy final. Okay. Um, and then we are looking for angular acceleration of or angular velocity of this omega here. Okay, at this point, what would be this omega? All right. So if we take the x rotation to be at this point, okay, then we only have to consider the rotational kinetic energy about the x going through this point. Okay, so let's call that to be point O. So then initially the rod is over here, it's being released from rest. So the initial kinetic energy should be zero. Okay, plus the energy done by so in this case, let's take a look here. So if we take this as the x rotation, so then there will be the gravity here, the mg, okay? And then there will be supporting force coming out from this joint point. But it could be like O normal, O tangential, okay? It can have two components. But you are taking this as x rotation, so then the moment by these two forces should be zero, okay? Because R is going to be zero, all right? Now the tricky part is about this one. So as this guy goes down here, all right? So if the angle, we can take the angle like, let's see, we can take for a given moment, say the rod is to be here. So then this angle is theta, okay? So then the moment by the gravity over here, you can do it this way, okay? So you can do like the force mg times r, so it will be 1/2 L times, okay, we will take the cosine of it because this angle now is over here, okay, this is the theta. You want to take the angle of r and then the g, so then you'll be doing cosine theta, okay. You'll integrate from 0 to 90 degree because the angle goes from 0 to 90 degree, okay. And then that's going to be equal to the, so this in this case, because the torque is changing according to angle, okay, so you can do that. So then it's going to be equal to 1/2 I, should be about this point O, all right. So for a rod, it's going to be 1/12 ml square. But if you the rod, this is I of G, okay, when it's rotating about the center of gravity. But if you look at one end, then that IO is going to be 1/3 ml square. Okay, so 1/2 I is about O omega square. Okay, now if you do in this integration or this, yeah, we should, let me see. Yeah, we should integrate with respect to d theta. Okay, so that's what we need to do here. All right, so if you do that, then we are looking at mg L over 2 sine theta, okay, from 0 to 90 degree, okay, on this side, equals to 1/2 of 1/3 ml square times omega square. So then 90 degree of sine gives you 1, and 0 gives 0. So on the left-hand side, it's going to be just mg 1/2 L equals to 1/2 1/3 ml square omega square, okay? So 1/2 here and 1/2 here can cancel out. The m can cancel out, okay? the L, just one L here, will cancel out the square there, okay? So at the end, this is going to be, now you can multiply both sides by 3 and then divide by L, okay? So 3g over L equals to omega square, take square root there, get rid of square root, get rid of square. So it's a square root of 3g over L, okay? So on this one, it's going to be B. All right. I think some of you guys didn't get this one right, but this is how you are going to do it, okay? So any questions you guys might have on this one? Okay. So if you are clear on this one, then we can move on. Looking at the example here. So this example says if this 50 kilogram wheel is subject to a force, all right, of 50 newtons, the radius of gyration of the wheel about its center mass O is KO equal to 0.3. It's asking you the angular velocity of the wheel after it has rotated 10 revolutions. The wheel starts from rest and rolls without slipping. Okay. All right. So let's external force here. Okay, we can figure out what's the work done by the external force. Okay. So then we can use principle work energy to solve the problem. Okay. So let's take a look. First, we want to look at the free body diagram here. In this case, there will be the weight of the wheel. There will be the normal force at the contact point here. There will be friction force here. Okay, so this friction force, if wheel is does not slip, which is the case here, so then this is a static friction. Okay, static friction is pulling the wheel forward in the forward direction. Okay, and static friction should not do work. Also, the normal force will not do work, okay? And then this guy, the weight is perpendicular to its translational motion, so 90 degrees. So then that means the weight does also not do work, okay? So the only work done should be by this pulling force P, all right? All right. So then we can solve for how much the work is being done by this force. You can do F times dr. Dr will be in this direction, the horizontal direction. So that means we'll be taking the putting the force here, P, it's horizontal component times ds, okay? So this is a constant force, all right? So then constant can go out of the integration. So you are doing integration to ds, the distance, okay? So distance should be 2 pi times r for 1 revolution, and then 10 revolution, you have 10 times 2 pi r, okay? So in this case, then the work done by this force is 1088, okay? So now, for the kinetic energy, initially the wheel is at rest, so T1 is equal to 0. For the final kinetic energy, because in the final kinetic energy, this guy, now it's moving horizontally as well as rotating about the point O, okay? So we should look at the kinetic energy in two parts, okay? So one is the center of gravity is having translational motion, so 1/2 mv g in this case would be O. So square plus 1/2 ig square, ig omega square, okay, rotational kinetic energy, translational kinetic energy, okay, so you add the two up. Now, because it doesn't slip, so then the linear velocity is equal to r times omega, okay? So then you can substituting v0 with 0.4 omega, okay? So then in this equation, or in this expression, you only have omega as an unknown, okay? So T2 is 6.25 omega squared. T1, then apply work and energy principle here. T1 is 0 plus the work done equals to 6.25, which is T2 omega squared, okay? Which 6.25 omega squared is T2. So then you solve for omega, okay? So divide both sides by 6.25 and then take square root to get the omega to be 13.2 radians. Okay. Questions on this one? All right. So if not, then we can move on the attention quizzes. Okay, 2 of them here. Let me so the breakout room is still open, but let me see. 2 of you guys were dropped offline, so I have to reassign you to the rooms. Okay, so all right, now you can go back to your breakout rooms and then work on these 2 quizzes. All right, so let's see. The first one, a disk and sphere. Okay, so it says both rows two full revolutions or two turns, full turns, which will have a larger angular velocity. Okay, so let's take a look here. So if both the rows down here for two full turns, okay, so then there's this gravity here, all right, and then there will be normal force. Okay, so if there's no slipping, okay, so there's, of course, there's friction force over here, which you don't have to consider because the work done by friction force, this is a static friction, so it should be zero. Okay, um, normal force and weight. Okay, so for two full turns, if the radius are the same, then the distance will be the same. Okay, so delta S will be the same. Let's see. So we can think about work done then will be only by the weight, okay, mg delta S, and then cosine of the angle, okay, theta. So if that's the angle theta, okay, in this case it will be sine, or theta is here, so sine of theta. I'm sorry about that. All right, then work will be the same. All right. Now the final kinetic energy. So T1 will be 0 again. This is the work down from 1 to 2 equals to this guy. T2 final kinetic energy, we should be thinking about rotational kinetic energy as well as the translational kinetic energy. So M 1/2 mvg squared plus 1/2 ig omega squared. And then because it doesn't slip, so vg is equal to r times omega. Okay, so this is 1/2 m r squared omega squared plus 1/2 I g omega squared. Okay, we can take 1/2 out, so mr squared plus ig times omega squared. Okay, equals to the same u1 to 2. Okay, plus 0. So T1 plus U1 to 2 plus T2, okay? So then we'll be looking at this expression over here. Now this is the same for both scenarios, okay? So they have the same mass, they have the same radius, so this is also the same. The only thing that's the difference is the Ig, okay? So then that will determine the W or the omega here, okay? So if one has larger Ig, then omega will be smaller. Otherwise, if the object have smaller Ig, then omega will be larger, okay? So we are looking for the larger angular velocity omega. So that means whichever has smaller I with its center of gravity, then that's the one, okay? Now for a sphere, I for a sphere is 2/5 mr squared, okay? I for a disk is actually 1/2 mr squared. So you can see for sphere, it actually is less than the disk, okay? So then sphere will have larger angular acceleration, angular velocity, okay? So because this is less than that, so then omega sphere is going to be bigger than omega of disk, okay? So sphere. So A will be the answer for the first one, okay? Um, for the second one here, it says a slender bar of mass m and l, length l, is released from rest from the horizontal position. The work done by its weight when it has rotated through 90 degrees is, okay? So we kind of did that on the first one, on the second concept quizzes over there. So that's the work done, okay? So it's going to be, you do integration of that, and then it turns out to be mgl over 2 sine of 90 degree, which is 1. Okay, so work done by gravity or the weight should be mg times l divided by 2. Okay, so this will be C on this one. Okay, all right. We kind of did that in terms of torque by the weight, okay? But if you just do it directly according to the work done by the weight, should be minus mg delta y, okay, in y. So delta y is equal to, in this case, delta y is equal to minus 1/2 L. Okay, so then that's also mg L divided by 2. Okay, so this is also C. So either way, okay, but you don't want to double count the work done by the same weight. Okay. Any questions you guys might have on this too? All right, if not, then I'll have you guys work on the group problem solving here, and then we can take a look at the solution a few minutes later, okay? So go ahead and join your breakout room again, and then work on this one, and then we can come back in a few minutes.
Dr. Ho. Dr. Ho, we had a question about
Uh-huh.
the length. So the radius of it is Ka equals 1.75, but then right there from A to G, what are we supposed to use as our radius if those are different?
Right, so Ka is the radius of gyration, which it doesn't have to do with the physical length over there. Okay, so Ka, you use Ka to calculate what's your moment of inertia. So if you do m times Ka squared to be moment of inertia about point A. Okay.
Okay. Yeah, that's right.
All right.
And then, so then we'd use the 1.25
Yeah, that's your R.
for the work, or do
For
we
for the distance, like the length mg times R times L, or yeah, whichever you want to call.
okay.
Hmm.
All right, thanks.
Okay.
I'm gonna head back to the breakout room. I just wanted to ask you about that.
Okay. Actually, I think there's option in the breakout room. You can like say ask your host question or something like that. You don't have to
Oh,
come out. So if you do that, then I will join your room.
okay,
Yeah, but
cool.
yeah, go ahead, rejoin your room. Okay.
Alrighty.
Mhm. All right, so let's take a look on the solution here together. So we'll apply again the principle of work energy, okay? So T1 plus U12 from 1 to 2 equals to T2. Initially, it's released from rest, so T1 is equal to 0, okay? The only thing does work here, if you take S rotation at point A, okay, then it will be just the weight, okay, mg times R, which will be from the the change in the center of gravity, okay, in y direction, okay. So it's so center of the gravity is 1.25 away from A. So when the angle is at 90 degrees, then that change should be 1.25, okay? Equals to 1/2 IA. If you take A as your x rotation, then it's only, we just only have to consider the rotational kinetic energy, okay? If you take the rotational axis going through G, then you have to think about both translational, the 1/2 mv square plus 1/2 ig omega square, okay? But if you take IA, then you don't have to consider that, okay? You actually combine the two in one here, expression here. I with A should be equal to m times Ka, which is radius of gyration about point A. Okay, that's what you use to calculate IA. All right, so then here you can see will cancel out. So then you'll be having G times 1.25 equals to 1/2 Ka 1.75 squared times omega square. Okay, so the angular frequency then is to be determined to be 2.83. Okay, so this one's kind of simple here, easy here. So any questions you guys might have? All right. If not, then I'll see you guys on Friday. Okay. Okay. Bye, everyone. Have a good day.
Dr. Hill,
See ya.
Yes.
I have a question on homework 11.
Mm-hmm.
On problem, hold on 1 second. On problem 5. When it was talking about, because it says that determine the rod's angular velocity at the instant when theta equals 40.
Mm-hmm.
So are we just ignoring like the 45-degree angle there and replacing that with a 40? Or are we going to find, like, because I started the problem, but then I kind of got confused because I didn't know if we were supposed to use that 45 angle as well and then use the 40 angle down the road later in the problem.
So the 45 angle, you don't actually have to use that one. You have to see like how much the center of gravity actually goes up. Okay, so use that to calculate the work done by gravity. Okay, it should be negative. And then also you want to use the 40-degree angle to see how much displacement is the object in the horizontal direction. Okay.
Okay.
Yeah.
So just replace the 45 angle with the 40 basically.
Yeah. So yeah, that's right.
Okay, thank you.
Okay, you're welcome.
Have a good day.
You too. Bye.